Thanks for taking the time to check out my poster on transactional storage class memory. I'm Ellis Giles, a student at Rice University. What is storage class memory? Well, on one side, we have a byte addressable dynamic memory, which is traditionally your L1, L2, and DRAM, and this is traditionally attached to the main memory bus, and it's byte addressable, but it's dynamic. If you turn off the computer, it's erased. And on the other side, we have block-based or persistent storage, which are accessed using volumes and blocks, and these are much slower, so hard drives, SSD, and flash. But wouldn't it be nice if we had something in the middle? And that's where SCM, or storage class memory, comes in. It's both byte addressable and persistent, and it operates on the main memory bus next to DRAM. As seen here, it's next to DRAM on the main memory bus, and it gives rise to new applications that can no longer have to rely on block-based persistence, but rather can operate on the persistent data on the main memory bus using traditional loads and stores. This gives rise to new applications such as in-memory databases, which no longer have to persist using serialized block-based persistence. But what's the problem? Well, suppose we're storing 4 variables A, B, C, and D, and we're doing them in order, A, B, C, and they're stored into the cache hierarchy. But now, what if one of the variables was evicted from another application writing to the same cache line? B would be evicted and overwrite it in main persistent SCM out of order. So instead of having A, B, C, D, we now have just B in persistent memory, and if this was a complex data structure, it could be corrupted. Likewise, if we were to write all the variables in order and flush them through the cache hierarchy, we still could have a crash before the last write. So even though the stores can complete, they can be corrupted in the middle. And it could leave memory in an inconsistent state. So what are some solutions to this problem? Well, we can do logging, but that can be a slow or synchronous or copy on write based undo log type operation, which slows our applications down. Luckily, there are some other techniques called SOFRAP, which generally do aliasing, so we can do redo logging and capture writes to specific addresses so that the out of order problem from cache evictions just go out of order to an NRAM alias table and can be erased. And after the transaction is complete, then these can be written to main memory. There's also hardware support, which enables catching these cache evictions in main memory before they go to these persistent SCM. But what does this look like for programmers now wishing to write a parallel program? Well, a parallel program, traditionally you could use locks, fine-grained locking to lock individual variables, or use compiler-based atomics. New hardware transactional and software transactional memory systems allow for easier programming and higher parallelism with using either hardware support or software support. But these have the problem that when at the end of the transaction, all of these variables are visible in main cached memory. And this brings us back to the problem where an out-of-order cache eviction, or even flushing the memories out of cache to main memory, can lead to a corruption in the persistent data structure. So now programmers are then back to this problem of square one, where they have to do a synchronous operation to persist those variables in main SCM. So how can we achieve the high parallelism with persistence without having to revert to slower methods? And that's where transactional storage class memory comes in. And this idea sprung from a course I took at Rice University, and adapting the method I developed for SOFRAP, which catches them in an alias table, and HardWrap, which is a hardware support on the back end of a main memory controller to catch cache evictions. And this leverages off of 2 techniques: a technique using Intel's restricted transactional memory, or a transactional locking approach. And I'll go through both of those quickly. The API looks somewhat similar to a software transactional memory, wrapping both reads and writes with begin and end semantics. With a Intel-based or restricted transactional memory support, remember all the variables once a transaction complete, are visible instantaneously. So what do? Well, on a transaction begin, we create a log, then we do the hardware begin, and then reads and writes proceed normally, with writes writing to a cached area of the log. At the end of the transaction, the hardware transaction closes, all the variables are visible instantaneously, and the log is committed. And we can operate in 3 modes. A background thread can also retire this log in the background or retire directly from the cached variables. The 3 modes are using a write log, so after the immediate complete, the log is committed. But during the log write, we could have an out-of-order cache eviction from the original variable. A log set reset, so where the reads and writes are operated on in the log area, so that they are basically aliased like the software app approach, and it's safe on transaction commit. Or a third approach where the log writes are instead due to a streaming store location. But on some architectures, this can cause a transaction abort because the transaction semantics capture those reads in the cache hierarchy. Or we can use a software-based approach. So in this approach, I modified transactional locking, and I did so in 2 ways. In transactional locking creates a write set, so when variables are encountered, they're added to the write set, and it periodically revalidates the read set. So the reads keep track of the version number that the application has read inside of the transaction, and those are validated to make sure that the read variables aren't changed. So this can operate in an encounter mode, such that as variables are written, the locks are acquired in the encounter order. And this is like an undo log. So as the variables are encountered, the lock is acquired, they're written, but the write set becomes an undo log. In a lazy mode, the locks are acquired only at the commit time. So the write set is built in an auxiliary part of the memory. And this is similar to a redo log. And at the end of the transaction, the redo log makes sure that no values have changed, and it rewrites the values. Reads have to consult the write set to make sure they have the latest values. And what I've evaluated on was the Stanford Transactional Applications for Multiprocessing benchmarks. And in one of the benchmarks, here's an example here. I found that the RTM-based with the thread-based retirement performs the best until it reaches a certain point, and that all of those hardware-based threads have to serialize. They start conflicting and serialize through a common lock. Forward work involves creating a more robust solution that has a forward lock that has a global fallback lock. In conclusion, we found that the TSCM is highly quick, fast, achieves high performance, and combines transactional memory techniques. The TLT2 lazy approach performs the best under high contention, with the HTM with the RTM-based thread retirement performs best under slightly lower contention. Forward work includes evaluating on different architectures and optimizing the global fallback lock. Thanks for checking out my poster at SC, and I hope to see you